In today's lesson, we are going to be looking at linear and quadratic functions. So this should be a review from previous years because you did look at linear equations in grade 9 and 10, and you did look at quadratics in grade 10. So hopefully this is a little bit of a review. We aren't going to go too much in depth into them. We're just going to look at the basic features of both. We are going to introduce a new term. Now you may have seen this term before, possibly in grade 9, but if not, we're just going to kind of recover it, and that term is the degree of a polynomial. So we've talked about polynomials before. In previous lessons, we've looked at adding and subtracting them. Basically, it's just a bunch of terms separated by addition or subtraction. So we could have an equation or a function that is a polynomial. Now the degree of that polynomial is the greatest sum or addition of the exponents in any one term. So we're going to look at the exponents in any one term, and the largest sum that we have, that's considered our degree. Now one thing to keep in mind when we're dealing with the exponents, it's the exponents on the variables. So the exponents on the letters. So if I go through and I look at my equation here, or my expression, 5x squared plus 3x plus 7, well, I can see here the sum of the exponent on this one is 2. The sum on this one is 1, because again, if we don't see an exponent on the letter, we assume it's an invisible 1. And on this last one, it's a degree of 0, because we don't have a variable at all. You could argue, well, x to the power of 0 equals 1, which is kind of what's occurring here. So that makes that variable disappear. So the exponent is 0. And then again, remember for this one, x to the power of nothing is the same thing as saying x to the power of 1. So again, just some things to remember. So the highest sum of exponents that we have is 2. So therefore, the degree of this polynomial is 2. One thing to keep in mind, if you have an equation that's not in standard form or it's not expanded, right? So in some quadratics, it might not be expanded. You can't determine the degree until it is in standard form. So determine the degree when it's in standard or expanded form. So you need to expand it so we can actually see what the degree is. So just something to keep in mind or be mindful of. If we're looking at comparing a linear function and a quadratic function, these are the things that we should find that separate the two. When we look at a linear function, it has a common first difference. A quadratic has a common second difference. Linear has a degree 1, quadratic has a degree 2. Linear, graphically, it's straight, so it should look something like that, generally speaking. And for a quadratic, graphically, it is a parabola. Now, we want to be careful with curve, because it is a curved line, but remember, a parabola is something where it's the same on both sides. So it could look like that, kind of a U shape, or it could look something like that, almost like an N. And those are generally the two basic forms that we'll see. So again, that's just separating the difference between linear and quadratic. Now we're just going to look at some different representations and see if we can identify what type of function it is. So first we're going to look at simply equations, and we're going to see if the function is linear, quadratic, or neither. So what we need to do is look at the degree, and from there we should be able to determine linear or quadratic or neither. So if I look at my first function, I look at the exponents and look at the value of the exponents, on the variables. So this has a degree of 2. This has an exponent of 1. This has an exponent of 0. So the highest exponent is 2. So this is a degree 2, which means it is quadratic. If I look at the next one for b, 3x plus y equals 5. Well, the exponent is 1 here, the exponent is 1 here, here the exponent is 0, the highest exponent is 1, so that means that the degree of this equation or function, the degree is 1, therefore it's linear. If I look at the next one, look at the variable, I see the exponent 3, look at the variable for the second one, there is no variable, so that means it's an exponent 0 or degree 0. The highest degree is 3, so that means this polynomial has, or function has a degree 3, which means it is neither. So it's neither linear or quadratic. Technically it's a cubic function, but we won't touch on that too much, or we won't touch on that in this course, as long as you know that it's not linear or quadratic. If I look at this one, f at x equals 2 to the power of x, here I have an x, it does have an exponent of 1, however, in this case, x is the exponent, or the variable is the exponent is a variable. Actually, that's probably a better way to write it. Exponent is a variable. So because the exponent is a variable, we can't talk about the exponent on the exponent. So this would be an example of neither. Right? The variable has to be part of the actual term, not the exponent. So this is neither, and technically this is actually an exponential function, which we will look at later. Last one, f at x equals 1 over x. So right now the x has an exponent of 1, but if we remember back to grade 9 and grade 10, when we look at power laws, to get 1 over x to the power of 1, we had to have had x to the power of negative 1. So that means the degree or the value is negative 1. So you might say degree negative 1. Usually we don't talk about negatives in terms of degrees, so this would be neither as well. This is actually what we call an inverse function. So that's how we can tell if it's linear or quadratic, by looking at the equation or the function. Now we're going to move into looking at table of values. So this is where we have to understand what first and second differences are. Again, hopefully remember from grade 9, maybe even grade 10, but first differences basically means I take the difference of the first two values. So 2 minus 5. Right? Bottom minus the top. 2 minus 5 gives me negative 3. Then I look at the next pair. Negative 1 minus 2. I get negative 3. Negative 4 minus negative 1. I also get negative 3. Negative 7 minus negative 4. I get negative 3. So the values that I get when I subtract, these are what we consider our first differences. If we were to take the difference of these numbers, similar to what we just did, we would be finding the second differences. But I don't need to go that far, because we should notice that our first differences are all negative 3. So because our first differences are all the same, because they're the same, then that means this is linear. Because that was one of the characteristics of a linear function. Let's look at the next one. Doing the same thing. bottom minus the top. 2 minus 1 is 1. 4 minus 2 is 2. 8 minus 4 is 4. 16 minus 8 is 8. So looking at our first differences, they're not the same, so it's not linear. I can do one more check by looking at the second differences. So 2 minus 1, so taking the answers that I found and doing the same thing. 2 minus 1 is 1. 4 minus 2 is 2. 8 minus 4 is 4. So when I look at the second differences, we should see that, again, our second differences are not equal. So when neither first or second differences are equal, or it's not one or the other, that means the function is neither linear or quadratic. So it's neither. Looking at my last example, again, same thing with first differences. Go through. 1 minus 0 equals 0. Again, remember it's bottom minus the top of our two pairs. 4 minus 1 equals 3. 9 minus 4 equals 5. 16 minus 9 equals 7. So if I look at my first differences, again, they're not the same. So from there, I should know that it's not linear. I can check to see if it's quadratic by taking the second differences. So, 1 minus 0 is not 0, it's 1. Go through, take your second differences. 3 minus 1 equals 2. Next one. 5 minus 3 equals 2. Last one, 7 minus 5 equals 2. So now, our second differences, these are all the same, 2, 2, and 2. So, our second differences, our second differences are the same. Therefore, it's quadratic. So that's what we're looking for from a table of values to see if our function is quadratic, or to check if it's quadratic. We take the second differences and they should all be the same. We're going to go through the same thing, just given an equation. We're going to go through, put it in function notation, come up with a table of values, graph it, and see what type of function it is. So function notation, we talked about that before. All that does is replace y with f at x. So this becomes f at x equals 2x minus 4. So that's all the function notation is. It's just replacing this y with f at x. For a table of values, here we can go through and we're going to plug in our points. So for example, y equals 2 times negative 1, or, minus 4. I'm going to stick with my function notation actually. F at x, or f at negative 1 is equal to 2 times negative 1 minus 4. Negative 2 minus 4 is negative 6. And if I go through, I should find 0. I get negative 4, then negative 2, and then finally 0. So I'm plugging in the value for x and solving. And again, you can go through and do that for the last two. So there I have my tables of values. I could look at the first and second differences, but let me just go straight to graphing it. Right? Because I could also look at the equation or the function notation to find the degree to see if it's linear or quadratic or neither. But let's graph it and see what we get. So we have our first point at negative 1 and 6. Negative 1, negative 6. Then we have 0 and negative 4, 1 and negative 2, 2 and 0. So I have my points. I can connect them with a straight line. And we should see that we have a linear function. The points form a straight line. So that means if we were to go back and do the first differences, they should be the same. And in our function, we can see that we do have a degree of 1. Looking at the next example, h equals 2t squared minus 4, our function notation is going to be a little bit different. Because we're not dealing with y or x, we're dealing with h and t, we're going to have to write it slightly different. So we're going to say h at t instead of f at x is equal to 2t squared minus 4. So a slight change to the function notation, but same general idea. For the table of values, we can do the same thing. H at negative 2 means 2 times negative 2 squared minus 4. We can go through and calculate that. And get a value of 4. If I go through and do the same thing, but plug in negative 1. So 2 times negative 1 squared minus 4. Get negative 2. 0. H at 0. So 2 times 0 squared minus 4. We should get negative 4. Plug in 1. Should get negative 2. And plug in 2, we should get 4. So sometimes there is a way to tell if it's quadratic as well by looking at the values. If we kind of see a repeat or a repetition, right, to a certain degree, only one repetition, and we'll talk about why later in a future lesson. But when we see some repetition, it should indicate that we might have a quadratic function because we know what type of shape it makes. It's that U shape or that parabola. So we do have a repeat of numbers to some degree. We could also check the first and second differences, but let's just go right to our graph. So we have negative 2 and 4, negative 1, negative 2, 0, negative 4, 1 and negative 2, and 2 and 4. If I connect my points here, we can see that we do have a parabola or that U shape, so this is indeed quadratic. If we were to check our second differences, we would find that it's quadratic. We can see from our function notation as well that we do have a degree 2. So again, the main thing from this is just understanding the key differences between a linear function and a quadratic function, as well as how to use those characteristics to identify each type. It should be a review from grade 9, so hopefully this wasn't too difficult or wasn't too new.